Good afternoon, everyone. Thank you for attending today's webinar on sample preparation methods to ensure accurate X-ray fluorescence analysis. My name is Jordan Rose, and I will be your moderator for today's webinar. I'm an application specialist for XRF here at Oxford Instruments. Just a few things I'd like to mention before we get started. Please note that we are recording today's event, and each of you will receive an email with a link to the recording of today's webinar sometime tomorrow. If you are having difficulty hearing us from your computer, please check to see that the volume is up or consider calling into the webinar via the phone. The dial-in information for today's webinar is 1-855-749-4750 for the toll-free line, or 1-415-655-0001. The access code is 669-295-816. You'll find this information on your confirmation. All of your lines will be muted during the duration of the webinar. Feel free to ask questions throughout the event by typing your queries into the box located in the chat window. Please send all questions to all panelists. We will respond to as many questions as time allows. For those questions that we cannot get to because of time constraints, we will be sending the answers via email. Today, we will be hearing from Andrew Bates Harrison. Andrew is a technical support specialist for XRF here at Oxford Instruments. Hi, Andrew. Thank you for being here today.
My pleasure, Jordan.
And without any further delay, I'm going to hand the platform over to Andrew.
Hi, everyone. My name is Andrew Bates Harrison, and today I will be covering different types of sample prep for X-ray fluorescence applications. These are just some of the industries that run more smoothly and efficiently using XRF technology. In this presentation, I want to highlight the importance of proper sample prep and how it impacts analysis. First, I will answer the question, what is X-ray fluorescence? Then how and why sample prep is important. This is a little introduction to some of our instruments. From left to right, we have the XMEC 7000 series. These handheld analyzers are great for their versatility and portability. The X Supreme in the middle is used for bulk analysis of liquid, powder, and solid samples. And the Xstrata 980 on the right is used to measure thickness and composition, commonly used in printed circuit boards or in the plating industry. XRF works on the atomic level. X-rays are produced from the spectrometer and excite the analyzed volume within the specimen. The incoming X-ray ejects an electron. When this happens, the atom becomes unstable until an electron from an outer shell fills the vacancy. Once this happens, it generates a characteristic X-ray equivalent to the energy difference between the inner and outer shell. Each element will have a characteristic X-ray of a specific energy, and this is how one can determine what elements are present in the sample. The detector collects these characteristic X-rays and displays them as a spectrum, which is a visual representation of the composition of the sample. By looking at the x-axis, one can see the energy range goes from 5 keV to 10 keV. And as the energy increases, the atomic weight of the element increases. This is because the electrons of the heavier elements are bound tighter. On the y-axis, there are counts, which is the number of X-rays. One can see that iron is present in a large quantity compared to the other element because of the high number of counts. Another important aspect of the spectra is the background level. This is the level at the base of the peaks. One can see that the background increases around 8 keV. It is important to limit the effect of the background if you want accurate analysis. This can be done by using a primary filter. This component will be covered briefly in the next slide, or one can also correct for the changing background by using corrections once the calibration model is created. This is the setup in a typical XRF instrument. The X-ray source can either be a radioactive isotope or an X-ray tube. The X-rays excite the sample, and the detector interprets the energy and amount of characteristic X-rays. In this example, we also have a primary and secondary filter. Primary filters are typically used to lower the background level, which is caused by scattered X-rays. Secondary filters work by filtering out a specific element. These types of filters are only required if the detector doesn't have the resolution to separate adjacent peaks. Once a set of calibration standards is measured, one can then create an empirical calibration. The standards of known concentration are measured and the intensity is stored. A linear regression can then be created, which follows a straight line model, y equals mx plus b, where m is the slope and b is the y-intercept. More often than not, the simple straight line fit will not create the best model because there are other influences from adjacent elements and also other matrix effects. Proper sample prep along with correction factors for any interferences will ensure the best possible calibration model. This way, when the intensity of the unknown is detected, it can be compared to the intensity of the stored standard to give a calculated value. Another way of creating a calibration is using FP, or fundamental parameters. This slide shows the Sherman equation, which is a typical FP equation. These equations can become quite complex, but they can produce a result without using any standards at all. FP uses absorption coefficients for each element in the measured intensities, along with other parameters to calculate a result. One can often make an FP calculation more accurate by adding a standard called a type standard. One type of calibration is not better than another. They have different advantages. If standards aren't available, then FP is a better option. FP is typically more versatile and can cover a large range of concentrations in many different elements. An empirical calibration, when using proper standards and sample prep technique, will give more accurate results. Empirical calibrations are also better when traceability back to a standard reference material is critical. Now that the basic principles of XRF and the different type of calibrations have been discussed briefly, the details of sample prep and sampling will make more sense. What is sampling? Sampling is what we are most interested in for our analysis, and it is important that the sample be representative of the bulk material. From the sample, you then create a specimen. The specimen is what is actually placed in the instrument for analysis. Finally, within the specimen, there is an analyzed volume. Since the final results are only based off of the relatively tiny analyzed volume, one can see how important it is to practice sound sample prep techniques. The following graph shows the depth that can be analyzed by a typical XRF instrument for certain elements. One can see that the thickness varies by element, but it also varies by other factors, such as density and the absorption coefficient of the sample. There is a maximum thickness and also a minimum thickness that show the limits of the XRF. On the high end, we can see that the X-rays do not penetrate very deep into a sample. At this maximum level, we find that when the sample becomes thicker, the instrument does not detect a higher level of excitation. In other words, the count rate doesn't increase. This concept is referred to as infinite thickness. In this example, if we look at chromium, after about 25 micrometers, the sample is infinitely thick because the detector does not see any difference in the sample. The depth in which the X-rays penetrate, multiplied by the area of the X-ray beam, is the analyzed volume. Here is an example of how XRF analysis can be impacted by the analyzed volume. In this example, 2 particles of aluminum oxide are within the analyzed volume. If an imaginary line is drawn representing a second analyzed volume, there are 5 particles of aluminum oxide. This is an example of a specimen that may not be ready for analysis due to the particle size effect. Grinding and pressing can reduce the particle size effect. The same picture can also be used to show the mineralogical effect of a sample. This time, it is assumed that both the green and blue particles represent silicon dioxide, but here they are in two phases, or crystalline structures. There are many structures of silicon dioxide. For this example, alpha quartz and beta quartz was used. These two structures have different physical properties, which may lead to different sensitivities. This mineralogical effect is small compared to the particle size effect. Grinding and pressing can reduce the particle size effect, but the only way of eliminating the mineralogical effect is through creating fusion beads. If fusion beads aren't an option, it is important to make sure that the standards used for calibration are made up of a similar structure as the actual unknowns. These standards may sometimes be difficult to acquire, so that is why it's always a good idea to have a backup set of standards that are actual production samples, which are measured by a different form of analysis. This will give you more confidence in your results. Grinding plays a vital role in reducing the effect of particle size. Grinding works by making all of the particles in the specimen a consistent size. The picture here shows a tuck mill. In general, these mills can be made of hardened steel, agate, or tungsten carbide. The choice of material will depend on cost and type of contamination you potentially introduce to the specimen. Tungsten carbide mills, for example, have been shown to reduce cobalt at a 5 ppm level to a 7-gram silica sand sample during 4 minutes of grinding. Grinding times will also vary sample to sample, so testing should be done in order to see if the grinding time chosen is adequate. Grinding time can be increased in specified intervals and retested. The optimum grinding time can be found when the analysis does not change significantly when more grinding time is added. Harder samples will generally require more grinding time. A grinding time of 5 minutes is typical for raw meal cement and finished cement, and 4 minutes is typical for silica sand. The following two slides show a real-world example of the impact of grinding. Here we have 12 samples of fertilizer and 3 specimens of each. The samples were received in a loose powder form. We can see that the average standard deviation for these 10 measurements was 0.228%. This slide shows the same 12 samples after being ground in a tungsten carbide tuck mill. 20 grams of sample were weighed out, and the samples were ground for 2 minutes. After grinding, the average standard deviation dropped down to 0.171%. That's an improvement in repeatability of 25%. After the sample is ground to the appropriate size, it can be measured as is, or it can be pressed into a pellet. Pressing pellets generally gives better results than running a loose powder. Pellets are generally pressed at 15 to 20 tons per square inch, which produces a flat, smooth, dense sample for testing. Once the pellets are held at this pressure for about 30 seconds, the pellet can be carefully removed. The pellet should now be around 3 millimeters thick. If the sample is thinner than this, consider using more samples. The opposite is true if the sample is much thicker than 3 millimeters. Again, consistency is key, so the sample needs to be weighed before pressing. When creating a pressed pellet, sometimes a binder is used. Binder holds the material together to make a more resilient pellet. Binder is typically free of contaminating elements because it contains a very light matrix, elements that can't be detected by XRF. The binder needs to be stable under irradiation and vacuum conditions. types of binder can vary from liquid to solid. Starch and ethyl cellulose are some common examples of binder material. Since binder contains such a light matrix, it usually makes little difference in the absorption of X-rays in a sample containing an average atomic weight matrix. It can, however, increase the background due to scattering, which may reduce sensitivity for light elements. This is why it's important to only use the minimum required amount of binder, if any. When making a pressed pellet, one should use about 7 grams of sample. The binder should be added after the initial grinding and then ground for an additional 30 seconds. This two-step method of grinding was proved to produce highly homogeneous and resilient pellets. Agglomeration or caking may occur if the binder is added in the beginning of the process. Agglomeration can also occur if the incorrect amount of binder is added to the sample. The correct amount of binder should be about 5 to 10% of the sample weight. It is extremely important to use the same amount of binder in each standard for calibration and in each unknown. Any deviation from this ratio may decrease accuracy for analysis. Here one can see some pictures of the typical setup for pressing pellets. On the right there is the die set. The sample is placed in between the two discs. Then the plunger is inserted on top, and the whole assembly is carefully placed in the press. Here one can press and hold the sample at 20 tons of force for about 30 seconds to reveal a smooth pellet. The die must be cleaned thoroughly between each pellet to reduce contamination and for ease of operation. The die can be cleaned with plastic dishwashing scores. Do not use anything abrasive or metal for cleaning, as this can harm the die surface and affect the consistency of the pellet. As discussed, in order to reduce the effects of inhomogeneity and particle size effect, you can grind and press the pellet. When the accuracy and precision of your results is most important, consider making fusion beads. The beads are made of a small ratio of sample to flux. The ratio is critical to analysis and will affect both the speed of the reaction and the way the sample is absorbed by the flux. The ratio of sample to flux can range dramatically, but the first and a commonly proposed method uses a ratio of 1 to 100. The different phases inside the sample, alpha and beta quartz, if we go back to our previous example, will undergo a chemical reaction to create a more uniform or completely non-crystalline glass-like structure that is ideal for analysis. The chemical reaction involves heating the sample and flux to a temperature of 800 to 1,000 degrees Celsius in a crucible. Crucible material can also vary, but an alloy of platinum plus 3% gold is hardly wetted. This reduces cleaning time and contamination. Making fusion beads leads to better accuracy and precision over the pressed pellet, but it should be mentioned that since the sample is diluted, the detection of trace elements may not be possible. Both products are commonly fitted with a sample spinner in order to rotate the sample during analysis. The sample spinner is used when measuring powder, pellet, or fused bead samples. The sample spinner effectively increases the spot size as well as helps to minimize the effects of inhomogeneity in the sample surface. Once a calibration is created, the sample spinner is set up to run automatically. XRF is essentially a comparative method, so it is very important that standards and unknowns are measured in a consistent way. The direct analysis of a sample is certainly possible and easy to perform, especially with the handheld XRF. Using a handheld has its advantages, as it eases the load on the lab and often leads to quicker decisions. Measuring samples in the field will often require some sample prep. This type of sample prep can be as simple as ensuring that you are measuring a flat, smooth surface each time. It is also important to measure many test points and gathering enough data for accurate results. Looking at the sample of rock, one can see the different test points, and an average of 4 measurements will certainly give the analyst a better picture of what is in the bulk material over a single measurement. Drill core analysis and mind mapping are commonly done using handheld analyzers. Miners can use the data collected to determine how deep to dig or to find the next location for a potential expansion of the mine. FP calibrations are used when little sample prep is required, like in the rock and core samples seen here. The option to create empirical calibrations with more sample preparation techniques are available if more accuracy or a lower limit of detection is needed. Grinding samples, pressing pellets, or creating fusion beads would all be potential options for this type of material. The XMET analyzer also has the ability to positively identify different alloys. There is an extensive grade library within the instrument, and the operator has the choice of using alloy mode, which automatically selects from a list of stored calibrations. Some of the alloys include nickel, cobalt, aluminum, stainless steel, and many others. Alloy mode selects from both FP and stored empirical calibrations, which are traceable back to standards. Sample preparation for these types of metals is simple. Sanding, polishing, grinding, and cutting can all be done with the ultimate goal of producing a flat, smooth, homogeneous surface without contamination. This is most important when measuring aluminum alloys, since this is a light element. When measuring coat weights on paper, it is important to use a paper stage. One typical calibration is silicone on paper, which is used as a release liner for stickers and labels. The paper stage is made of metal, which works to reduce the background by providing a heavy matrix to absorb the X-rays. The paper is placed on the paper stage with the coated side out so that it faces the detector and X-ray tube. It is important that the same base paper be used for all standards, and a blank or sample without any coat weight be used as an instrument correction. This way, if the base paper does change, a new blank can be cut and measured to correct for the difference, usually seen as a difference in background. When a large amount of fluid is available for analysis and the concentration level is too small to quantify, certain concentration techniques can be done. The nuclear power industry uses filters like these to test for soluble and insoluble metals in the coolant water. This technique has also been used to extract and test for zinc and lead in air. Pouring dilute liquid samples into a standard liquid powder cup will not work unless there are a detectable amount of analyte. But by using filters, these analytes can be concentrated and easily detected. The concentration of analyte in the fluid can then be back calculated by using the total volume of liquid passed through the filter. In order to use this calculation, it is assumed that the entire sample is excited because it is contained in a thin film. Since most oils contain a high enough concentration to measure directly, they can be analyzed simply by pouring oil in a sample cup prepared with sample film. Different factors can affect the accuracy of the oil analysis. Oils will have a matrix made of light elements like carbon and hydrogen, which tend to scatter X-rays and produce more background, which reduces the sensitivity. These effects can be exaggerated when the viscosity or density of this oil matrix is varied. There are corrections that can be applied to compensate for this change in background, but it is important to make sure that the standards being used for calibration are similar to the actual unknown samples. Care should also be taken to shake the standards or measure the samples quickly to avoid settling. Another example of a matrix effect can be illustrated by measuring used and new oils in the same calibration. A new oil will have unused fuel additives, but a used oil will have the additives plus decomposition products and small metal particles. In order to prepare this used oil sample for analysis, it may be required to filter the oil or use a centrifuge to remove any solids. Matrix effects can also be reduced by diluting the sample, but this may reduce detection of trace elements. The use of sample film is also required and does reduce sensitivity. Sample film is another important part of sample prep for liquids and powders. Sample film is a transparent layer of protection needed to shield the detector and X-ray tube from the sample. The sample film needs to be clean and free of contamination. In the oil industry, this is especially important as customers are usually dealing with small concentrations and tight limits. The sample film also needs to be robust and resistant to petrochemicals and solvents. All of these factors are weighed to determine the correct sample film for the application. These are some of the examples of the films that are most common. Polythor is the highest transmission film that is used. It is important in the wear metal application when measuring light elements like sodium, magnesium, or aluminum. These elements are found in ppm levels in oils and are especially sensitive to film type and film thickness. When a thick film is used, it absorbs more counts, which leads to an instrument that is not able to measure low levels. Mylar is a robust film that is used for the fourth row elements, in which the cleanliness and thickness of the film are less important. Sometimes film has special properties that are more conducive to better analysis than others. Poly-M is used for sulfur determination because there is no contamination from silicon. Silicon can negatively affect the results due to the proximity of sulfur on the periodic table. This just serves as an illustration for the different types of film. One can see that after about 6 keV, which is iron, the type of film used really doesn't matter at all. After 6 keV, all of the film types shown here have about the same transmission. The type of film used is most important around 1 keV, which is the sodium level, and one can see a very big difference from the cation film shown in black and the polycarbonate film shown in orange. The transmission percentage is about 60% at 1 keV for polycarbonate, and there is barely any transmission at all for the cation at the same energy level. When making a sample cup for liquid or powder analysis, generally a second layer of film is used. This secondary window is used as a backup in case there is any leak from the main cup. The main cup is then placed inside the secondary cup. It is important that the film on both cups be free of any wrinkles or contamination. Once the sample is measured, the inner of the main cup can be disposed of and replaced with a new disposable inner. The film on the secondary cup must only be changed if contaminated or wrinkled. This is how the liquid powder cup sits in the sample carousel. There is a fill line about halfway up the inner. Even though the analyzed volume is much thinner than this depth, it is important to be consistent when filling the cup because of the packing density and other factors. Here we see that the main cup is within the secondary window, and this is placed inside the sample carousel. The X-rays have to travel through 2 layers of film, so it is even more crucial that the correct film be used. This diagram shows the sample preparation techniques covered in this presentation. There are many factors when deciding on the right amount of sample preparation for your needs. You must weigh up costs of the equipment and materials with the accuracy desired. If you are new to using XRF, start with less sample prep and move on to more advanced if your application is more critical. Thank you for taking the time to attend this webinar. I'll now hand it over to Jordan so that he can answer, or he and I can answer some questions.
All right, thank you, Andrew. That was a really good presentation. So we do have a few questions that came in over the chat, and you guys can feel free to send any more questions that you may have now, and we'll see how many we can get to in the next 5 or 10 minutes. And any questions we don't answer will be emailed to you separately tomorrow. So the first question we got here is, when do you need to use binder?
That's a good question, Jordan. Binder can be used when the sample is soft or it binds together more easily. So gypsum might be an example of a sample type that you wouldn't have to use binder. Typically with limestone or lime samples, we do use binder. And you can also tell, because when you create the pressed pellet, if it does crack or the surface does flake off, that will certainly impact analysis, and we try to minimize that.
Okay. Can you use more sample than 7 grams for making pellets? What's the maximum amount of sample you can use? And is it dependent on the pellet size?
It certainly is dependent on the pellet size. You basically want to strive for a pellet that's 3 millimeters thick. So after you grind the sample and you press the pellet, you can then see how thick the pellet is and estimate how much more sample you need to add so that the pellet can become 3 millimeters thick.
All right, what else do we have here? What is a type standard?
Well, a type standard is any sample that can be used to increase the accuracy of your results. So after you have a calibration line, you use a type standard to measure a sample that might not be measuring accurately. So an example would be if we set up a calibration for oils, and we were typically running a 5W30 oil, and it ran accurately. If you put a different type of oil, say a 10W30 or a transmission fluid, it might not run accurately because now you're comparing 2 types of oils that may have a different weight or viscosity. So you use a type standard to adjust for that difference.
Okay. What causes background in the spectrum?
Well, background is generally caused by, we call them tube lines, but basically energy from the X-ray tube. There's a filament, and that causes tube lines in background, but background is also just caused by Compton scattering and scattering of light elements. So anytime you measure a sample containing a light matrix, like oil, which is a hydrocarbon, or plastic, it'll generally produce more background.
Okay. And just got another question. When measuring light elements, such as aluminum and silicon, is there a big difference between using a fine powder, 300 mesh or so, compared to a pressed pellet?
There is a pretty big difference. I don't know if I could quantify that difference, but generally for the light elements, a pressed pellet will give you better accuracy over a loose powder, and that's because it's much more dense and you just have better transmission.
All right. And I'll take one more question. When you're measuring sulfur and oil with a thicker film, such as Mylar, how low could the limit of detection be for sulfur using a thicker film compared to, let's say, a poly 4?
Well, it looks around 5 ppm might be your limit of detection.
All right. All right. Well, thank you. Any other questions we didn't get to today? We will be, like I said, we'll be sending an email with the answers. And thank you all very much for attending our presentation. We hope you enjoyed it. And have a nice day.